Good day everyone, I am Joshua V. MARINDUQE, a student of University of Cebu main campus, currently on his 4th year mechanical engineering, and I'm here to discuss to you about composite materials, mainly the different types of composites and the different processes of composite materials. So what is a composite material? A composite material is a combination of two materials with different physical and chemical properties. And when they are combined, they create a material which is specialized to do a certain job. For instance, to become stronger, to become lighter, or resistant to electricity. They can also improve their strength and stiffness. The reason for their use over traditional material is because they improve the properties of their base materials and are applicable in many situations. Their lightness is also very important to automobile and aircraft industry because of this. Less weight means you have a better fuel efficiency and consumption. Some examples of composite materials includes concrete, fiberglass, mud bricks, rocks, and natural composites such as rock and wood. For the next part, I'm going to tackle about the different types of composite materials. To continue, it's common everywhere to notice the reinforced concrete used for constructions. But have you ever thought of the need of using it? Well, concrete is a material that has very good compressive strength, but it fails when a tensile load is applied on it. On the other hand, steel rods have good tensile strength. Now, when you combine these two materials, it gives us two reinforced concrete with improved tensile and compressive strength. Likewise, a large number of products have been developed and by combining different materials for obtaining enhanced performance. Such materials are called composites, and that's what we're going to discuss today in this video. We'll be discussing what composite materials are, why do we need it, and its classifications with some examples. Composites are multi-phase materials composed of two or more materials that are chemically distinct and can be distinguished by interface. The property of the composite material depends on the property of the constituent elements in the present context. Composite materials refer to artificially made materials, but some natural composites also exist. Wood is one of such good examples. For natural composite, wood is made of a number of strong cellulose fibers bound together by a stiffer material called lignin. But why exactly do we need these composite materials? Well, not all of the desired properties can be achieved by mere metal alloys, ceramics, and polymers. So we do need some materials with unusual combination of property, and that is where composite materials come into play today. Composites are extremely used in aerospace, underwater, and transportation applications. Most of the composites are made of two different phases. The continuous phase present throughout is called the metric phase. This surrounds and binds the second phase material called the dispersion phase. The properties of the composites vary according to the percentage size, shape, distribution, and orientation of the dispersed phase in the matrix. When it comes to the classification, composites are on three different types. There are particle reinforced composites, fiber reinforced composites, and structural composites. Let's discuss all three types one by one. Particle reinforced composite is a type of composite that uses tiny particles as its dispersed fate. These particles are characterized by their equal dimension in all directions. These particle reinforced composites are further classified into two types based on their reinforcement mechanism. They are large particle composites and the dispersion strengthened composites and large particle composites. The interaction between the phases should be treated at the continuum level. Here, the filler material replaces some volume of the material and modifies its property. The change in property depends on the volume of the filler material. Concrete is a very good example of this type. Here, cement acts as the matrix and sand and gravel acts as the particles. Another example of this type is cement, which are the composites made of ceramics and metals. When it comes to dispersion-strengthened composites, the phase interaction takes the place at the atomic or molecular level. Here, a certain level of fine material is added to a hard or strong material, like metals and metal alloys. The dispersed phase can either be metal or non-metal. An example of this type of composite is thoria, dispersed nickel. It's a type of nickel alloy that has 3% of thoria in it. The next type of composite is the fiber reinforced composite. Fibers are characterized by their length and diameter ratio. They possess high strength and stiffness, and the elastic modulus of fibers will also be greater than of the matrix. Fiber reinforced composites can also be further classified into two types based on the duration of the fibers. There are continuously arranged fiber reinforced composites and discontinuously arranged fiber reinforced composites. Of these two continuously arranged types will have an orderly alignment of fibers. In the second type, the fibers may either be perfectly aligned or randomly arranged. Let's move on to the last type of composites, which is the structural composite. Structural composites are made of both of homogeneous and composite materials. The properties of the composite materials depend on both on the material properties and the geometry of the composite. Structural composites can also be classified into two types. There are laminar composites and sandwich composites. Laminar composites are made of number 2-dimensional sheets that have high strength in a single direction. These sheets are stacked and cemented together in the orientation that is shown here. A well-known example for this type is plywood. Now, the last classification we have is the sandwich composite. In this type, lightweight core material is placed between two thick sandwich panels. The panels on the either side will be strong enough to withstand the applied load. These type of composites are used in application like roof, walls, and floors of the building. With this, we have seen the different types of composites, and that's it. Next part is the different processes of composite materials. Composites are made up of at least two distinct intended materials which together improve product performance and or lower manufacturing cost. Many materials, routinely designated by other terms, are also considered composites, including plated, clad, or coated metals. The term composite, however, has come to mean the material consisting of a matrix or base material and a reinforcement material. The matrix functions as a binder for the reinforcement and controls the physical shape and dimensions of the part. The primary purpose of the matrix is to transfer the load or stress applied to the composite to the reinforcement. The matrix also protects the reinforcement from adverse environmental effects. The reinforcement function is to improve the mechanical properties of the composite and is typically the main load-bearing element. Reinforcement is usually in the form of fibers or particles. There are numerous methods of producing parts from fiber-reinforced thermoset polymers, with the primary types being manual layup, automated layup, spray-up filament winding, pultrusion, and resin transfer molding. Manual layup is a widely used method of manufacturing a wide range of composite parts and components. The process begins with cutting the reinforcement materials to size. This may be performed using knives, scissors, disc cutters, power shears, rotary power cutters, saws, or lasers. A mold having the desired part shape is then coated with a release agent to subsequent part release. Composite manufacturing molds are commonly made of steel, aluminum, nickel, copper, or polymer matrix composites. Once coated with a release agent, a layer of resin called a gel coat may be applied to the mold and allowed to cure a tracky state. As the gel coat cures, the reinforced materials is prepared for application by impregnation with wet resin or matrix material. The impregnated reinforcement material is then placed on the coated mold surface and hand-rolled for uniform distribution. On removal of entrapped air, more reinforced material and resin are applied as needed in this manner until the required partings have been built up. This so-called welt layup method can be used with nearly all reinforced materials and is widely used to produce glass reinforced polyester products and sometimes glass reinforced epoxy products. Wet layup is also used for making composite molds. Layup can also be performed using pre-preg material. Use of pre-preg eliminates separate handling of the reinforcement and resin. Pre-preg reduce resin consumption and improve part quality by providing more consistent control of reinforcement and resin contents. However, pre-preg must be kept in refrigerated storage until use time to prevent pre-curing. Composites are made up of at least two distinct intended materials, a matrix or base material, and a reinforcement material. The matrix functions as a binder for the reinforcement and controls the physical shape and dimensions of the part. The primary purpose of matrix is to transfer the load of stress applied to the composite to the reinforcement. The matrix also protects the reinforcement from adverse environmental effects. Some of the primary matrix materials include polyester, epoxy, ismaili emmet, phenolic, and polyamide. The reinforcement function is to improve the mechanical properties of the composite and is typically the main load-bearing element. Reinforcement is usually in the form of fibers or particles. Some of the most commonly used fibers are eaglet and aramid and carbon, which is also referred to as graphite. These fibers come in many forms, including strand, tow, fabric, pre-impregnated or pre-preg tape, and free forms. There are numerous methods of producing composite parts, with the primary types being manual layup, automated layup, spray up, filament winding, pultrusion, and resin transferring molding. After production, composite parts may be allowed to cure at a room temperature or with open air heat assistant. Composite parts are also commonly consolidated and cured in heat plating presses, ovens, or autoclaves. After curing, composite parts can be cut, machined, drilled, and otherwise fabricated by many of the same methods used for metals. Additionally, composite parts may be joined and assembled using adhesive, bonding, and mechanical fastening.